distortions, also known as stretches and compressions, or sometimes called dilations and contractions. These deal with the opening or the widening of a graph, stretching it out side to side, or perhaps squashing it inward, or stretching it out vertically, or perhaps flattening it down. Now, the definition in the PowerPoint said this is accomplished by multiplication by a constant, a positive constant. In this case, we're taking the basic square root function and the square root function being multiplied by 3. By the definition, this should be a vertical distortion. Let's take a look. As with the other two, we recognize that if this is vertical, then x-coordinates are unaffected. So we're going to start with the same x-coordinate for each of these. We'll use x equals 4. Any x value will do, but again, we want to choose values that will be friendly to graphing, but also friendly to the operation in question. So we don't want to use 3 because we can't do the square root of 3 very nicely. But the square root of 4 we can do very easily. Now, in the transformation function, as with the vertical shift and the vertical reflection, we start by doing the same thing that we did here and producing even, at least for the moment, the same result. And then after we produce that original result, we make an alteration. The result here is that the output value is 3 times bigger, literally 3 times the original output value. Let's take a look at a different input value and see how that works again. Again, we will choose an input value that is very friendly to the square root, so let's try 9. The square root of 9 is, of course, 3. Now, in the transformation function, using the same input value, we again start the same way. The square root of 9 is, again, 3. And then we take that original output of 3 and multiply it by the 3 that is distorting the graph. And we get, again, an output value that is 3 times larger than the original. Note that in the first pair of values, it was f of 4 equals 2 with g of 4 equals 6. So note that these values did not go up by the same amount. If we look at it in terms of addition, like in a shift, this went up by 4, but this one's going up by 6. That's why it is a non-rigid transformation. A shift literally picks up every point and slides every point up or down or left or right the same distance. This does not, because that multiplication takes the distance above the x-axis and multiplies it. The larger the number we multiply, the larger that distance will be, and the larger the transformed distance will be. So this is not done by adding, this is done by multiplication. Let's take a look at the graphs of these two functions. Using the information we just got. But we only need the first quadrant really, because the square root function has a domain of 0 to infinity and a range of 0 to infinity. So no negative numbers involved here. Now, the original function, the square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. Now, in particular, I want to look at the two input values that we used before. X equals 4, which had a y value of 2, and x equals 9, which had a y value of 3. The idea then, as the distortion causes, is that we should see the distances above the x-axis become 3 times as big. So, if I were to take this arrow representing the distance and do it again, and then do it a third time, that should put me at 4,6, which is exactly the ordered pair we got from that. We can do very much the same thing here. Right now, this arrow represents a distance of 3. So we can go up that distance again, and then that distance again. And that puts us at 9. So, 9, 9. What we get here is a graph that is stretched out vertically. It still has the same basic shape in the sense that it still has this endpoint and extends to the right, growing very gradually, but increasing as we go. This one does it a little bit faster, but it still has the same basic shape of the endpoint and then extending out to the right, but flattening out eventually. So we have not changed the nature of the graph. We haven't changed its orientation. It's still aimed the same direction. We haven't changed its position in the sense that we haven't picked it up and slid it around so that it still has the exact same shape, the exact same dimensions. We've distorted it. We've stretched it out vertically. And that causes it to be taller. Let's take a look at horizontal distortions. We'll use a different basic function here. Excuse me. This time we'll use f of x equals x squared. And we'll use g of x equals 2x squared. So note that the 2 is multiplying the x before we get to the basic squaring operation. That classifies this as a horizontal distortion. Now, a horizontal distortion, a horizontal shift, or a horizontal reflection has no effect on the y value. So we start by picking a y value that we would get. So let's think of an ordered pair whose output value is going to be a perfect square, like, say, 4. And solve to find the x value, or in this case, 2 x values that produce that. So we toss in a square root over both sides, but remember that when we use a square root to cancel a square, we end up getting plus or minus 2. So we get 2 values. X is negative 2 produces a y value of 4, and f of positive 2 produces a y value of 4. Let's take a look at this one. Same output value, and we solve for x. Well, again, we're going to undo the square with the square root, again getting our plus or minus 2. Now, because there's more steps to take, it would be a good idea to split that into its 2 separate statements. Positive 2 equals 2x, and negative 2 equals 2x. And then we finish out by dividing both by 2. And over here, dividing both by 2. So the x values we get here are actually half as big as they were in the original basic function. that corresponds nicely with the way that we said in the PowerPoint that this works, that for a horizontal distortion, we actually divide the x-coordinates by this value. Because in solving for x, we divide by the value that's multiplying the x. So just like with horizontal shifts, where if you have an x minus 3, it actually goes to the right 3, because of the inverse operation. The inverse of subtraction of 3 is addition of 3. That's what causes us to go to the right. Well, the inverse of multiplication by 2 is to divide by 2, or to multiply by 1/2. So, let's take a look at what this looks like. Now you might ask, why am I labeling the x-axis in such an interesting way? Well, the fact of the matter is that if we're dividing x-coordinates by 2, anytime that x-coordinate is an odd number, we're going to get something that is a fraction or decimal. So specifically a half. So it would be a good idea to have those, the ability to mark those accurately. So the original function has its vertex at 0, 0. It goes through 1, 1, 2, 4, 3, 9. And on the other side, symmetric. So this would be the original basic quadratic function. Now, what we've got here is, at the y value of 4, we've got our two ordered pairs with x values of +2 and -2. Now, in the transformation function, we found that those 2 points were pulled inward. So the same y value, but half the distance away. The same y value, but half the distance away from the axis. So instead of going all the way over, we go halfway over, 1, 4. And x equals -1, 4. Now, with that in mind, we could visually do the same thing by looking at any of the other distances on here. Like, for example, this distance is a distance of 1. To go halfway out would put us here. And on the other side, the same thing. We go a distance of 1 space to the left, halfway out would put us here. And we could do the same higher up if we choose. But what we get is a graph that is narrower, that is compressed inward. Now, depending on how you look at this, here's an interesting thing about distortions that doesn't happen with shifts or reflections. And that is that depending on how you look at this, you might think of this as being steeper, as being taller, much like the square root function we saw in the previous comparison. It does seem not just narrower, it also seems taller. Well, that does make a certain degree of sense, and here's a little experiment you can try at home. Take a rubber band, stretch that rubber band out, and when you stretch it out in one direction, watch the other sides pull inward. So when we stretch it up and down, it narrows. That's actually kind of what happened here. The mathematical effect is a narrowing, but it does also kind of look like it's going up faster. And that is actually the case. Actually, algebraically, this is equivalent to 2 squared times x squared, which is 4 times x squared. This would be a vertical distortion. So a horizontal distortion by a factor of 1/2 is equivalent to a vertical distortion by a factor of 4 for this function. That's not going to be true for every single function. Everything's different. This was predicated on the idea that 2 squared was 4. If this had been a cubic function, well, it would work out a little differently, but the idea is that any horizontal distortion and any vertical distortion, they have corresponding ways to make them happen from the other point of view. That's actually kind of nice because, let's face it, horizontal transformations tend to be a bit of a pain in the butt. So it would be kind of nice if, and we can't always do this, but it would be kind of nice if we can kind of turn a horizontal distortion into a vertical distortion, because the vertical transformations are always easier to work with. They're always just a little bit nicer. So, we have an interesting thing here with distortions, but the graph is really important here because it allows us, to have it properly measured so that we can actually see the effect of the distortion. Shifts and reflections tend to be a little easier to visualize. Stretches and compressions, or in general just distortions, they can be a little bit tougher. But they work under very similar principles, namely that the vertical transformations still are very direct. If it says to multiply by 3, then you multiply the y-coordinate by 3. The horizontal transformations, always the inverse. If it says multiply by 2, you actually are going to divide by 2, or multiply by 1/2.